Hello, today I will be constructing proof for the Pythagorean theorem from the first construction on the Cut the Knot website. Here we will begin with an arbitrary right triangle, and this will be triangle A, B, and C. Our first step in this proof will be to construct squares with the lengths as the legs and the hypotenuse of our triangle ABC. So first we will want to construct a square with side length AC. So I'll do that for you right now. So here we have the square with side length AC constructed onto the leg of triangle ABC. We will go ahead and repeat this same process for the squares of side length AB and BC. So I've gone ahead and I've constructed those two other squares with side lengths AB and side length BC. The next step to our proof, we will want to create a line from A to line segment DE that is parallel to line BD. So I'll go ahead and do that for you right now. So here we have a line from point A to line segment DE that is also parallel to BD. Next, we're going to want to go ahead and construct a line segment from point A to point D. Also, we want to construct a line segment from point F to point C. So now that we have constructed these line segments AD and FC, we will attempt to prove that triangle FBC is congruent to triangle ABD. And this step to our proof may not seem like it may make much sense right now, but it will help us in the long run in trying to prove that the sum of these two squares, the legs of the right triangle, will equal the square of the hypotenuse. So we will start off attempting to prove that these two triangles are congruent. First off, we know that FB is congruent to AB because they are sides of a square, in which the sides of a square are all congruent. For the same reason, we know that BC is congruent to BD because they are sides of the same square. Now we will attempt to prove that angle FBC is congruent to angle ABD. So here we know that angle FBA is congruent to angle DBC because they are right angles, and we know this because they are angles in a square in which all angles of a square will equal 90 degrees and all right angles are congruent. Next, we know that angle ABC is congruent to ABC because they are the same angle. And we can see that angle FBC consists of the sum of angle FBA plus ABC. Likewise, angle ABD is the sum of angle DBC and ABC. Therefore, we can conclude that angle FBC is congruent to angle ABD because sums of congruent parts are congruent. In proving that these two angles are congruent, we are now able to prove that triangle FBC is congruent to triangle ABD by side angle side, in which FB is congruent to AB, angle FBC is congruent to angle ABD, and segment BC is congruent to segment BD. Now that we have proved that triangle FBC is congruent to triangle ABD, we know that the areas of these two triangles will also be congruent. Next, I want to prove that the area of triangle ABD is half of the area of rectangle DBML. The area of a triangle is 1/2 base times height, and the area of a rectangle is base times height. This triangle and this rectangle share the same base in BD, and because they are parallel lines, we know that they have the same height in either BM or DL. Therefore, the area of triangle ABD is equal to 1/2 of the rectangle DBML. Similarly, I would like to show that triangle FBC has area 1/2 of square BFGA. This is because they share the same base in FB and they share the same height in either segment BA or FG. Therefore, the area of triangle FBC will equal 1/2 the area of the square BFGA. Now we know that the area of triangle ABD is half of rectangle BMLD, and the area of triangle FBC is half of the square of square BFGA. Also, previously we have proved that the area of triangle ABD is equal to FBC. Therefore, by the transitive property, square BFGA has an area that is equal to BMLD. We are now halfway to our conclusion, and we'll have to do a similar type of proof in order to finish our desired proof. So I will start by hiding these two lines. And I will now draw in two other lines in line BK and in segment AE. We will now attempt to show that triangle BCK is congruent to triangle ACE. We will do this much similar like we did in the first part of our proof, in which BC is congruent to CE because they are sides of the same square. We also know that the angle BCK is composed of a right angle and angle BCA. Likewise, angle ACE is composed of a right angle and angle BCA. Therefore, angle ACE is congruent to angle BCK. Finally, we know that segment AC is congruent to segment CK because they are sides of a square. We now know that triangle BCK is congruent to triangle ACE by side angle side, in which BC is congruent to CE, AC is congruent to CK, and angle BCK is congruent to angle ACE. Therefore, we know these triangles are congruent. Also, their areas are congruent. We now know that segment AL is parallel to segment CE. Therefore, we are able to prove that the area of triangle ACE is 1/2 of the area of rectangle LMCE because they have the same base and the same height. Therefore, the area of the triangle is 1/2 of the area of the rectangle. For the same reason, we know that triangle BCK has an area 1/2 of the area of the square AHKC because they have the same base. These lines are parallel, so we know the distance between them is the same. So 1/2 the base times the height will be 1/2 the base times the height. Therefore, the triangle BCK has an area 1/2 that of square AHKC. We have previously shown that the area of triangle BCK is equal to the area of triangle ACE, and we have just shown that the area of rectangle LMCE is 2 times the area of triangle ACE, as well as the area of square AHKC is equal to 2 times the area of triangle BCK. Therefore, by the transitive property, the area of rectangle LMCE is equal to the area of square AHKC. We have now finished the second portion of our proof, and we will combine the results from the first portion and the second portion to get our final result. From our first portion, we have shown that the area of square BFGA is equal to the area of rectangle BMLD, and from the second portion, we have shown that the area of AHKC is equal to the area of LMCE. As a result, the area of square DBCE is a combination of the two rectangles LDBM and LMCE, which consequently is the sum of square BFGA and AHKC. Therefore, we have shown that the squares of the legs is equal to the square of the hypotenuse. Once again, the sums of the squares of the legs of a right triangle is equal to the square of the hypotenuse. Therefore, we have come to our desired conclusion, and we have completed this proof. Thank you.